Welcome once again in the class of design of steel structure. We are learning the design of built-up columns. In this lecture, we are going to see the design of column is for the combined axial plus bending. I am Mr. Sisugule, Assistant Professor, Civil Engineering Department. So, combined permissible axial and bending compressive stresses. So, as we know, uh, for the direct stresses, the P by A is the stress calculation formula, and for the bending, this is M by Z. So here no P is the force and A is the cross sectional area, as well as M is the bending moment and Z is the modulus of the section. So again we can convert this M into P, M is into P into E. Because of the eccentricity we will get this bending moment. So these kind of stresses will act on the column because of the eccentric loads also. So what we'll get is sigma AC calculated plus sigma BC calculated. That is axial compression, and this is compression due to bending. So what we have is we have to check it for sigma AC calculated divided by sigma Y plus sigma BC calculated by sigma Y should be lesser than or equals to 1. So here you can see uh, again we can modify this equation. Sigma AC calculated by sigma AC plus sigma BC calculated by sigma AC should be lesser than 1. This is nothing but the uh, permissible axial compressive stress, and this is the permissible bending compressive stress, and these are the calculated axial compression and calculated compression due to bending. Now we know already the Euler's formula, that is Euler's load, that is P equals to pi square EI divided by L square. We know I is nothing but the AR square, that is area into uh, square of the radius of gyration. So pi square E A R square divided by L square. So that becomes pi square E A divided by L by R bracket square. So we are converting into pi square E A divided by lambda, because L by R is the nothing but the lambda. So if we divide a P by PE, so what we'll get is P divided by pi square EA divided by lambda square. So again we are converting P by A into n sigma AC calculated divided by pi E lambda square. So n sigma AC calculated divided by this pi E lambda square is nothing but the FCC. So thus the maximum bending moment, bending compressive stress, taking into account the additional moment due to axial load interacting with deflection. So again, this sigma BC calculated divided by 1 minus P divided by PE equals to sigma BC calculated divided by 1 minus this P is nothing but the n sigma AC calculated divided by FCC. This P by P, where this FCC is nothing but the elastic critical stress in compression. We have learned this thing in the earlier curriculum, that is in the analysis part of the structure. N is the factor of safety in compression, as we have mentioned over here. Lambda is the slenderness ratio, and P is the Euler's load. So this 4.6 equation, again this equation we can write as sigma AC calculated divided by sigma AC plus sigma BC divided by this 1 minus n sigma AC calculated divided by FCC into sigma BC. What we are doing? We are uh, adding the additional moment due to axial load interacting with deflection. So what IS 800 says, so it recommends the above interactive formula with a factor of safety n as 1 by zero point 0.6 and incorporate the reduction factor, that is Cm, to consider the end conditions other than the equal column end movements and side sway of the column in frames, which should be multiplied by the amplified bending stress ratio. Thus equation 4.7 can be rewritten as, here you can see, sigma AC calculated divided by sigma AC. Here what we are doing, we are modifying this thing again. So 1 minus sigma AC calculated divided by zero point 0.6 FCC into sigma BC. So what you are doing? You are taking this n as a 1 by zero point 0.6. Now again, this equation can be extended to make applicable compression member subjected to axial load and the bending moment on the both the axis. This is for the single axis. Again, we have added Cm also over here. That thing we need to consider, and this should be lesser than 1. This is the formula from the code, so we are extending it into biaxial bending moment. So what we'll get is sigma AC calculated by divided by sigma AC, then CMX divided by BCX calculated divided by 1 minus sigma AC calculated divided by zero point 0.6 FCCX into sigma BCX plus, this is for other axis, that is CMY sigma BCY calculated divided by 1 minus sigma AC calculated zero point 0.6 FCCY into sigma BCY. This should be lesser than or equals to 1. Then in additional, if the additional movement due to axial load interacting with deflection are neglected as per this IS 800, the ratio of sigma AC calculated divided by sigma AC should be lesser than or equal to 0.15. So we are reducing this 4.9 equation as sigma AC calculated divided by sigma AC plus sigma BX calculated divided by sigma BCX and sigma BCY calculated divided by sigma BCY should be less than 1. So where the sigma BCX calculated, it is the calculated bending moment bending compressive stress due to bending moment at the major axis. Sigma BCX permissible bending compressive stress about major axis taken into account the lateral instability. BCY calculated the calculated bending compressive stress due to bending moment about the minor axis, and BCY, that is permissible bending compressive stress about the minor axis. And this XX and YY are the major and minor axis respectively. So these are the derivations. Basically for the this design we don't need any derivations. Here the in IS 800, the in section 7 for the combined stresses the combination has been given, that what we have derived the formula has been given over here, that is sigma AC calculated divided by sigma AC, CMX BCX calculated divided by 1 minus sigma SC calculated zero point 0.6 FCCX into BCX, and CMY B sigma BCY calculated divided by 1 minus sigma SC calculated into divided by zero point 0.6 FCCY into BCY should be lesser than or equals to 1. Again, that same thing has been given over here, that is the ratio of sigma SN to sigma AC calculated to sigma AC is less than 0.15, then we can modify this expression like this. So all the things has been given over here. Only thing is we have to use or check these conditions for the combined uh, axial compression and bending. So as far as that derivation part has been concerned, that is only for the understanding. Only you need to remember is the formula which has been given in the IS 800. So now we'll see design of the eccentrically loaded columns. So eccentrically loaded columns are subjected to direct and bending stresses. The following procedure may adopted for the design. So step 1, the allowable working stress in compression is assumed and the cross sectional area required for the axial load is computed. As we have seen in design of the compression member or the column, we need to calculate this the area required for the axial load. Then the calculated sectional area may be increased by 50 to 100% account to eccentricity of the load or for handling the bending moment, additional bending moment. Then we have to choose the suitable section from IS handbook or the steel table. The slender ratio of the column should be worked out. From this table number 5.1, we have to check the allowable compressive stress for the calculated slender ratio. Then this compressive stress sigma SC calculated, we need to calculate it by dividing the load with the sectional area provided, that is sigma SC calculated equals to P by A, and this bending stress of the column calculated by dividing the bending moment with the sectional modulus, that is sigma FC calculated, equals to m by z. So once we calculate the sigma AC and sigma BC, we need to check these conditions, and if the this column has been passed in or safe in these conditions, hence the design is okay. So this is the design of eccentrically loaded columns. Now the splice. A joint when provided in the length of the column is called as a splice. Splices for axially loaded compression member require detailed addition. If the member is loaded concentrically, no splice is required. Actually, we are providing the support only to avoid the slip from that section from one another. Otherwise, it is not required. The compression will be transmitted by direct bearing, and the column sections could rested one on top of each other and function satisfactorily because they are under compressive load. However, the load is never truly axial, and the real column has to resist bending due to its eccentrically applied load. In addition to this, the column may be subjected to the bending moment. Also, the bearing surface of the adjacent sections can never be machined to the perfection. The meaning of this statement is, when we are putting, suppose this is a column and that ends over here, and we are putting the another column, and for this we require a splice. What will happen if you observe, this is the I section, this is the end of the I section, that is it ends over here. If you see, this end is not perfectly straight or not as the finished surface, which is called as the machined. So some gap has been removed over here. If you put this column on the another column, so what will happen, there will be some gap or something like that, something like this. So obviously the edges are not coinciding or some gap will be there. So because of this we need to provide a splice to transfer this load. Otherwise what will happen, the stress concentration where this column touching each other, there will be a stress concentration, and the chances of crushing at that point will be there. So thus the adjoining pieces must be positively connected. The column section can be spliced in following cases. The first is when the length of the column is more than the length of the column section available. That is, in market, if we have the uh, available section is less than what we required, so again we have to go for the splicing. A number of pieces can be joined to furnish the full length of the column. And in case of multi-story building, the section of the column required for the various story may be different as the load goes on increasing for the column for the lower story. So in multi-story building, obviously if you see the multi-story building like this, so these are the different stories. So by adding every story, the load will be added for the column. Likewise, if you consider this column, so only load from this top floor is coming on this particular column. If you consider this column, so load from this above story as well as additional load by this story is coming on the column. So providing the single section for entire length is not economical. So again we have to reduce the section as we progress on the upside. That is, we have to provide a small section over here as compared to the section at the bottom. So for this we need different sections, and to connect those sections we require the splice. So here you can see the uh, a different type of splices. So first is the column flanges having the complete bearing, as we have discussed. Here the column has identical sizes, so they are resting on each other in a quite a good manner, so no need to provide any packing or something like that. So only two plates for this connection has been required over here, As you can see, this is the front view, this is the side view, and this is the web splice. And over here, additional web splice has been provided at this point. Now the column flange is having the partial bearing. So you can see the web has been rested over one another, and this section at the top is having small area or different section is there. So we have to provide the packing over here. As you can see, even the this flange area is also less. So again we have to cut the plate like this, and we have to provide the packing. And for this case, column flanges over the web of other column. So what here we are doing, we are providing a bearing plate over here, and again we are resting the next column on this particular bearing plate. So we are connecting it the angle over here, and we are providing the packing over here. So these are the some types of the splices. Now the design. So the first step is to ascertain a nature of the load to which the splice is subjected. They are axial compressive load, bending moment, or occasionally shear. For the axial compressive load, the splice plate are provided on the flange of the two column sections to be spliced. If the column has machine dents, the splice is designed only to keep the column in position, as I have told you earlier, and to carry the tension due to bending moment to which it may be subjected. The splice plate and the connection should be designed to carry 50% of the axial load and the tension, if any, due to bending moment. If the ends of the column are not machined, the splice and the connection are designed to resist total axial load and any tension if present due to the bending moment. So, the load P1 for the design of splice and the connection due to axial load P on the column will be P by 4 for machined ends and P by 2 for the non-machine ends. So the load due to bending moment, that is P2 equals to M divided by this E, that is lever arm, where the lever arm is center to center distance between two splice plates, and P2 is the load due to bending moment. The splice plates are assumed to act as a short column and with zero slenderness ratio. So we can provide full allowable compressive stress, that is 0.6 Fy. The cross-sectional area of the splice is calculated by dividing the load coming over the splice by the allowable compressive stress. The width of the splice plate is usually kept equal to the width of the column flange, and the thickness of splice plate is found by dividing the cross-sectional area required to the width of splice plate provided. And in case of bearing plate is to be designed between two column sections, the length and width of the plate kept equal to the size of lower story column, and the thickness is computed by equating the moment due to load to the moment of resistance of the plate section. Few notes has been given over here. If the joint is subjected to a bending moment along with the axial load, the splice plate is provided on the flange. The total load which splice and connection are designed will be sum of the axial load and load due to bending moment, that is P1 and P2. The rivets are also checked for tension. When shear force act in addition to gravity load, the splice plate provided on the web, as the web takes the maximum shear stress. Then the splice should, as far as possible, is so placed that the central axis of the splice coincide with the central axis of the member joint. This is done to avoid the any eccentricity. Likewise, like this case, the CG of these both sections coincides. Even in this case also. If packing are provided between the splice plate, the column flange additional rivets as per IS specifications are provided. The specification has been given for the packing in IS 800 that we need to check, and additional rivets has been provided for the packing. So this is for today's lecture. Thank you.